Okay, let's continue. Our second speaker is Shaoyun Bai, and he's going to tell us about the overconvergent intertwiner and the p-adic gamma.
All right, thank you for the introduction and thanks for the invitation. I'm very happy to be here. So that's the title of my talk, Overconvergent Frobenius intertwiner and p-adic gamma class. And this is based on joint work with Pomerleano and Seidel. So this talk has 4 parts. So the main point of this talk is to formulate a conjecture. And the first 2 parts are going to be about getting preparations to make this conjecture precise. So in the first part, I'm going to introduce some basics about differential equations over a p-adic field. And in the second part, I'm going to introduce the mean conjecture. We call it the p-adic gamma conjecture. It has some similarity with the famous gamma conjecture, but I will discuss that in that part. And in the third part, I'm going to tell you about some evidence of this conjecture, mostly in the context of toric varieties. And it has many connections with mirror symmetry in the toric context. And also something about, say, cohomology of varieties over some fancy coefficient field that's called Dwork cohomology. And in the last part, I'm going to talk about some further problems. For example, what kind of examples we can expect for the conjecture to hold and how it connects to other fields like fluid homotopy theory. So overall, this is a talk about introducing some arithmetic aspects, the study of the differential equation to its mirror symmetry context. Okay, let me get started. So let me introduce some notations. So for this talk, I'm going to work over the field of p-adic rational numbers. So you can think of it as a completion of the rational numbers under a norm, the p-adic norm. Oh, the completion of Q under, I will just write things formally in the following way. So given a rational number, we can write it as a ratio between 2 integers. And its p-adic norm is going to be, we take p to some power, the power is going to be the following. We take the valuation of b under p, so you find the prime factorization of your number b, and there's going to be a power of p, you take that power, so that's valuation over p, and then you minus the valuation of a. Okay, so the point is, if this number is very divisible by p in the sense that, say, b is coprime to p, but it has a lot of powers in p, it's going to be very small. And if there's a large denominator in the sense that the denominator has large power of p, it's going to be big. So that's the point. That's going to be a norm, and we're going to define QP as a completion of the rational numbers under this norm. So inside this field, there's the range of integers called the p-adic integers. And for this talk, we are going to study differential equations over such fields, but we are going to study things over a slightly larger field. So we are going to do a field extension of QP, introducing a further variable called u, mu. And mu here is going to be a primitive p root of unity. So in other words, we're doing a finite degree algebraic extension of QP by introducing a new variable mu, and mu satisfies the equation that mu to the p is equal to 1. And it's a fact that actually this field has a different presentation. Instead of working with this variable mu, we can work with another variable called pi. It's not a pi as 3.1415, etc. It's just the notation people use in this field. And it satisfies the equation that pi to the power p minus 1 plus p is equal to 0. So this is something introduced by Dwork, and that's his notation. And another fact is that the range of integers of this field extension is going to be zp with pi adjoint. Okay, so that's the coefficients I'm going to work with. So now I can talk about differential equations over such fields. So consider the following thing. I'm going to look at connections with one single variable, and it's going to be a connection with a regular singularity. So I'll write things in the following way. So it's connection. So I write T over there to indicate that there's going to be a pole. and it has a form that's equal to t partial t plus at. And at here is going to be a power series with coefficients in matrices. So I'll write that in the following form. At is equal to a0 plus a1 t plus a2 t, etc. And so I require that first ai, that's right, and in general, ak t to the k. So for the coefficients, I require that it's going to be a matrix with entries inside QP mu adjoint. So that's our field. So it's going to be matrix of size R with coefficients inside here. And also I require that the leading term is nilpotent. Okay, so that's the setup. So we are working with a connection with one single variable, so it's in particularly flat. And in other words, all this condition is saying that we have a flat connection over the formal power series ring with coefficients inside its field, and it has a regular singularity. Okay, so we're going to look at flat sections of such a connection. So that's what I mean by a differential equation. So now I'm going to make a definition. It's something special, well, in this p-adic setting. So t is just an auxiliary variable, formal variable. Yeah. So let f be the Frobenius map, which takes its formal variable t to its pth power. And so what's the Frobenius intertwiner? Well, we have this map, and we can pull back our connection by this map. So Frobenius intertwiner is going to be an isomorphism between the pullback connection and the original connection. So maybe more precise, Frobenius intertwiner is the same as an isomorphism. I'll call it phi intertwining the two connections. So the first connection is Frobenius pullback. The second one is original connection. Okay. And concretely, in this setting of one single variable, it's the following information. So i.e., we ask that to be a formal power series with the property that, so it's an isomorphism. So in this setting, we're asking the leading term to be invertible. So phi 0 is in GLR of my field. And on the other hand, it's a map intertwining two connections. So it means that it's going to be horizontal if you put one connection on one side. So you're going to satisfy an equation, and the equation concretely is the following. Okay, so if you just unpack the meaning of that is intertwiner between two connections, this is what it means. So just satisfy some equations involving the original connection coefficients. Also, if you see the last term, there's going to be a pth power of the variable t. Okay, so that's the definition. And continuing this definition, we call this phi to be overconvergent. Convergent. provided that the convergence radius of this formal power series is going to be greater than 1, strictly larger than 1. So in other words, write it more formally. So we're asking that this quantity, so lim sup of n, we take the nth root of the p-adic norm of the nth coefficient of this formal power series. We ask that to be greater than 1. Okay. So this is the definition. Any questions at this point? Okay. So let's see an example. We consider simple setting. So that's going to be the situation where the coefficients are all, say, matrices of size 1. So they are scalars. So for r equals 1, we look at the connection with the regular singularity of the form nabla t partial t is equal to t partial t plus a constant times pi. Okay, so speaking, we are not exactly in the setting that this is going to be nilpotent, but let's just see how things work in this example. And if you do a computation, you will see that the following thing is going to be a Frobenius intertwiner for this particular connection. It's going to be e to the power pi times c times t to the p minus t. So this is going to solve this equation defining that to be a Frobenius intertwiner. Right, so if you check this equation, so mu is the root of unity. So 1 has valuation 0, so has p-adic norm 1. So any root of unity always has p-adic norm 1. And if you look at pi, it has a property that is p minus 1 power is going to be minus p. Minus p has valuation given by 1, p-adic norm given by 1 over p. You take it, well, divide it out by, the valuation out by 1 over p minus 1. Take the p to that power is going to give you the norm. Okay. Going back to this, so I was saying that this particular function, e to the power pi times c times t to the p minus t, is going to be a Frobenius intertwiner for this equation. And the fact is the following. So fact, this e something, if you write it as a power series, that is overconvergent. So phi t in this setting is overconvergent if and only if c is an integer. Okay. So already in this simple example, it's telling you something non-trivial. So it's only for a particular choice, the set of choice of the constant c, that you can get this better convergence behavior. Okay. And I'd like to mention that this function, which maps t to e to the pi times t minus t to the p, is called the Dwork exponential. So have you? Yeah, right. But also, you're looking at things like t minus t to the p. There's some kind of cancellation in between for this kind of n factorial coefficients you will see in the Taylor expansion of e to the t. So there's something to check here. Right. Yeah. Maybe, but we're going to stick to the setting where it's nilpotent because it's going to come from geometry and it's going to be quantum connection. It's always nilpotent. Yeah. Okay. Right. Okay. So if you have heard about this thing called the Artin Hesse exponential, it's the Dwork exponential is going to be like the first order approximation of that. But let me not get into that. Okay, so that's this example. Another thing I want to mention is that so if you assume this power series has a property that all their coefficients would take value inside the p with pi adjoint, or maybe I can ignore the pi for this discussion. Let me ignore the pi here. So in other words, I ask all the coefficients to be p-adically integral. This only implies that the convergence radius is 1. convergence radius. Okay, so you may wonder, for example, integrality is a very strong constraint for such a power series, but when we discuss about convergence, only have integrality will only tell us that convergence radius is 1. But overconvergence is asking the convergence radius to be greater than 1, strictly greater than 1. So it's something non-trivial. Okay. So, all right, going back to our study of differential equations, we can ask ourselves the following kind of question. So, given a p-adic differential equation in this setting, so how to find an overconvergent Frobenius intertwiner? And so, of course, you could say that, okay, having this kind of extraordinary convergence property is already very interesting, but you may ask yourself more, okay, so given such a Frobenius intertwiner with good convergence behavior, what can we do with it? So what is it good for? Okay, so that's the motivating questions. So that's the first part of the talk. That's the point of this talk. We'll see. Yeah. Right. All right. So next part, I'm going to go back to something we're more familiar with. So let omega be a closed monotone simplex manifold. So for simplicity, I will normalize my omega in a way that it's strictly, well, the cohomology class underlying that is the first term class over manifold. So if you're algebraic geometer, you can just think omega as a smooth Fano variety over the complex numbers. So for such a guy, we can define a class of differential equations that's going to be the differential equation from the small quantum connection. So I'm going to use the following notation. So my Q is going to be the Navikov variable. And my connection is the following form. So it's going to be a connection with a regular singularity and 0. And it's going to be Q partial Q plus the quantum multiplication with the cohomology class underlying symplectic form. And in this special setting of Fano varieties, it's a fact from symmetry topology that all the coefficients of this multiplication of this on the matrix coefficients, they are going to be integers. But of course, since now we are working with rational, p-adic rational numbers, it doesn't really matter if we have this very refined behavior that all the coefficients are integers, but it's going to be useful for other purposes. Okay, so that's our quantum connection. And remember, at the beginning, I introduced this variable pi, and it turns out that it's very important to work with a kind of different variable other than q. So we're going to work with the following variable. So consider t is equal to q over pi, where pi is the pi at the beginning, so pi to the power p minus 1 plus p is equal to 0. And we're going to rewrite our quantum connection in this new variable t. So it has a form t partial t. And the leading term, remember, the quantum product is a deformation of the ordinary cup product. The leading term here is going to be the cup product with a cohomology class represented by omega. And there's no t power here, so if we do a change of variable from q to t, it doesn't matter, it's still there. And this is also the setting that this term is nilpotent because omega has degree 2. So it kills everything if the degree is high enough. And continue, the terms in general are of the form pi t to the kth power times with this kind of notation. So this means that we're looking at the moduli space of rational curves such that its underlying homology class, when it pairs with the first term class, it's going to be 2K. So I'm just writing things in this kind of component-wise way. Okay, let me rewrite that. Yeah, my students always complain about my handwriting. Yeah. So we're summing for all integers, which are at least 1, and the terms are of the form pi times t to the kth power, and follow it by doing the quantum multiplication with the cohomology class underlying omega. And I write things degree-wise in the sense that this is going to be the contribution of all those rational curves whose underlying homology class. When we pairs that with the first term class, it's going to be 2K. Okay. All right. So this is our flat connection. We are going to study flat sections of this flat connection. That's our differential equation. So before I say the conjecture, I'm going to introduce another thing. Definition. This is the so-called p-adic gamma function. So it has many definitions. I'm going to use the following one, which has the better connection with the original gamma function. So we know that gamma function, of course, you can write it as an integral of some sort. It has a behavior that if you look at, say, integers, you evaluate your gamma function integers, it's going to be some factorial. So it satisfies this function equation that gamma s plus 1 is equal to s times gamma s. And the p-adic gamma function has a similar behavior, but it's different. So it's defined the following way. It's going to be unique. Oh. It depends on the power. Oh, that would be great. Do I need to connect that to the Bluetooth? Okay. Okay, so several steps, and it's not even my iPad, so. Sorry about the mess.
Okay, now it should be connected.
Oh, great, thank you. Thank you, Bern. Okay, great. All right. Yeah, I insisted that I don't want to use slides, and you see the consequence. So, okay, what's the p-adic gamma function? It has a following characterization. It's going to be a unique continuous function, say, going from ZP to the invertible elements inside ZP, such that the following function equations hold. So we're going to consider, in any case, if we go from Z to Z plus 1, so gamma P of 1 plus Z, it's going to be minus Z times gamma P at Z if Z is invertible inside ZP. So pretty much like what you see for the gamma function. However, if our Z is divisible by P, we just ask that gamma P at 1 plus Z is equal to minus gamma P at Z. Okay. And these properties will determine gamma P by continuity. So that's the p-adic gamma function. So I want to say a remark here. It turns out that the p-adic gamma function is closely related to the Dwork exponential. In the sense that, well, you can do some sort of expansion of your p-adic gamma function. You will see the coefficients, and those coefficients can be reconstructed from the Taylor coefficients of the Dwork exponential. And this is going to be a pretty important feature in later a later part of the computation. But those are something you are supposed to know about p-adic gamma function. So some functional equations and also some relation with Dwork exponential. Okay. So why do I introduce that? Because I'm going to introduce the following characteristic class. So definition. So let E over M be a complex vector bundle of rank R. So because the complex vector bundle, we can talk about its chain roots. So the p-adic gamma function is going to be just like how you define the gamma hat class. You're going to take those chain roots and look at 1 plus its chain roots, evaluate it as a variable inside the p-adic gamma function, then you multiply them together. So then we define gamma p of E to be the product for I going from 1 to R of gamma p evaluated at 1 plus Ci. Okay. And for the case of manifolds, we define the p-adic gamma class to be the p-adic gamma class of the tangent bundle. Okay. So this is some multiplicative characteristic class we can define out from the p-adic gamma function by looking at its chain roots. Yeah. Okay. All right. And now with this p-adic gamma function, I can say something further. So we consider the following endomorphism of the cohomology of the manifold. It's going to be a modification coming from cup product with the p-adic gamma class. So we have to do some rescaling according to degree of cohomology classes. So it has the following behavior. It maps a cohomology class called the alpha to the following thing. We're going to consider the following operation. So p to the power minus degree over 2, it means that take cohomology class, consider its degree, put it in the degree factor, divide it out by 2, and take its, well, p to the minus of that power. So that's the first step. And second step is to, well, I said second step. The first step is to take the cup product with the p-adic gamma class. Okay. So this is an endomorphism of the cohomology of a manifold M. All right. So far for monotone manifolds, I've introduced the quantum connection. I've also discussed things about the p-adic gamma class. And at the beginning, I talked about Frobenius intertwiners and its convergence properties. So now we can state our conjecture. So conjecture. So shamelessly, we call that the p-adic gamma conjecture. So the first step, first part of conjecture says the following thing. Okay, I think I forgot to mention something at the beginning of this talk. So remember, I said that the Frobenius intertwiner is going to be some power series satisfying some differential equation. And because we are working over a field of characteristic 0, it means that this power series is going to be determined by its initial term. So in other words, if I ask, say, a Frobenius intertwiner to have a particular form as its initial term, it determines this guy uniquely. So I point this out because this is going to be entering the formulation of this conjecture. It says that the Frobenius intertwiner for the quantum connection. So it satisfies this equation. So identifying the Frobenius pullback of its connection and the connection itself. So with the condition that its initial term, so phi0 is equal to phi0, where our phi0 is this guy here. So take cup product with p-adic gamma class and followed by this degree scaling according to P. So this Frobenius intertwiner is overconvergent. Okay, so that's the assertion. So in other words, we're saying that you can cook up some generating series from the quantum connection and its initial term, and you ask that if you look at, say, p-adic valuations of the coefficients of this guy, it has to grow in some way. Okay. And remember, there's a question of, okay, so suppose that we do have overconvergence, but what can we do with that? And the second part is supposed to be an answer, partial answer to this question in this context of quantum connection. So we also conjecture that, so remember, overconvergent means that the convergence radius is greater than 1. So in particular, you can evaluate your map, your Frobenius intertwiner, at a root of unity. So we're saying that the p-adic valuations of the eigenvalues of my phi and mu, so mu is a primitive piece of root of unity, it's going to recover the Betti number of the underlying manifold. So in the following sense. So it's a matrix, it has eigenvalues. We can count eigenvalues with multiplicity. And in the p-adic setting, we can also look at valuations of these eigenvalues. So the p-adic valuation together with its multiplicity is going to recover the dimension of the cohomology of that particular degree. So that's the assertion. Okay, any question about this statement? Yeah. Right. So for this conjecture, nothing. Right. Yeah. But we don't expect, for example, in a Clavier setting to have overconvergent behavior. Okay. Any other questions? Okay. So that's a conjecture, and let me say a theorem. So same group people, and I think it's pretty cool to call it BPS. Right. Okay, so it says that conjecture 1, part 1 of this conjecture, holds for toric Fano varieties. And Grassmannians. Okay. And the part 2 of this conjecture actually follows from some earlier work on holds for CPN and the Grassmannians. Okay, so there's some evidence for this conjecture. And it's pretty much like what Tony and other people did when they first formulated their conjecture for the original gamma conjecture for more or less for this same class of examples. Okay. So before I talk about the proof of the theorem, I'm going to say a bunch of remarks. Yeah. That's a great question. So, the gamma conjecture usually stated in the Fano setting for the U variable, and that's going to be more or less the Q connection when you're looking at the point at infinity. And in any case, from this perspective, the gamma conjecture is very analytic in the sense that it involves some analytic continuation going from 0 to infinity. But for this conjecture, it's only near 0. So it's already of a very different nature. That's the first thing. Second thing is that, so, when people conjecture the gamma conjecture, it comes from some observation like, if you look at, for example, the equivalent order class of constant loops inside the space of loops, by some renormalization procedure, you're going to see the gamma function. So that's why there is some physics justification of gamma conjecture. But for the p-adic version, it's also clear. And this actually goes back to the question of, okay, what's the relation between a gamma function and p-adic gamma function? So there were some kind of indications in the previous literature back in the 80s or so, but it's not so clear. Right. Okay. All right, so going back to remarks I want to say. So first thing is that, so we're in the monotone setting, and if you look at our connection, it's going to have an irregular singularity and infinity. So in particular, it means that our connection cannot come from geometry in the sense that it's not going to be a Gauss-Manning connection of some family. So this means that, if you have this Gauss-Manning setting, and if you can do some kind of multi reduction or p-adic extension of your families, then over there's a geometrically defined Frobenius, and you can look at this effect on cohomology. And that's sometimes how people cook up Frobenius intertwiners when the connection comes from the Gauss-Manning connection. But in our setting, our connection has a irregular singularity and infinity. Well, it's not so clear how to use this kind of machinery to construct this Frobenius intertwiner. So that's one subtle point. And the second part of this remark is about some history of this result. So although things weren't stated in the exact way as we formulate that, but in the case of CP1, this is a result due to Dwork, published in 1974. And I guess, let me say something further. Then in the case of CPN, it's a result due to a student of Dwork, Sperber, published in 1977. And well, their paper was sort of formulated in a way that it looks like they're studying some kind of Bessel function hypergeometric series. There are fundamental solutions to the quantum differential equation associated to projective spaces, and things are set in that way. Okay, so that's like the initial results in this direction. And then after that result, not so much is really proven about constructing Frobenius for connections with irregular singularity. But there is a notable recent work by Da Xinxu and Xinwen Zhu. They studied something called the Frankel-Gross connection. So some connection with representation theory origin, but for us, at least for some of us, the reason that we may care about that is there's some result telling you that from this connection, you can really relate that to the quantum connection of the flag variety. So their result is of similar form, that you have overconvergent Frobenius, and the p-adic valuations of the Frobenius eigenvalue at root infinity has some meaning. And then there is a theorem due to Lamb, I believe, telling you that you can go from the Frankel-Gross connection to the quantum connection of the flag variety. So combining these observations, they can lead to some form of the result that we conjectured, but its translation is currently missing. But I'm just saying that these are like the previous known results along these lines before us. Okay. That's the next thing I'm going to say. Right. Right. So if I call P the fundamental solution, yeah. Okay. I didn't make a precise statement, so I don't need to be precise on anything. So. Yeah. Right. Yeah. Good. So let me call P the fundamental solution of the quantum differential equation. So in other words, it's an automorphism which conjugates your connection to the classical part of the connection. Then if the initial value of the Frobenius is given by phi0, then the Frobenius intertwiner is out of the form. So then phi is equal to psi t composed with phi0 composed with psi at t to the p inverse. Okay, this is just some fact you can prove by looking at the differential equation. So in particular, we know that in the context of quantum connections, there is a given to construction of fundamental solution, which is based on looking at genus zero gravitational invariants with gravitational descendants. And because of its form of the Frobenius, we know that morally the coefficients of the Frobenius intertwiner is going to be some sort of linear combination of gravitational invariants. So this conjecture predicts that these gravitational invariants is going to have some interesting behavior about how divisible they are as powers of p. So p divisibility of gravitational invariants, which is also clear to us just from its definition. Okay. All right. So the last remark I'm going to say is in the Calabi-Yau setting. So in this case, for the Q connection, it's going to have regular singularity everywhere. And there are some conjecture formulated by Van Straten and collaborators predicting some integrality behavior of the coefficients of the Frobenius intertwiner, but also with initial term given by the p-adic gamma class. So roughly speaking, the conjecture is that, so now we don't work with this new variable t, we work with q. So working with nabla q partial q, then the Frobenius intertwiner phi with phi0 given by phi0, which I mean that it's going to be the cut product, the p-adic gamma class of tangent bundle, followed by degree scaling according to the degree. Then it has integral coefficients, p-adic integral coefficients. Okay, so it's kind of a different nature compared to the Fano setting, but still, the appearance of p-adic gamma class should dictate something very non-trivial. In this Calabi-Yau setting, it's integrality. Okay. Any questions about the theorem, conjecture, and remarks? Yeah. So there's no conjecture in the literature said in that way. So that's my interpretation. And it's a paper by, I remember, then do you remember all the people? Van Straten and who? I know, but do you remember the names? Okay. Della Osa, okay. Okay, I'm not sure I'm spelling things correctly, but you get the impression. Right, so they set things on the B side. They look at the B side coordinate. So which means that their conjecture compared to this one, well, if you think they're equivalent, actually assumes the integrality of the mirror map, and which of course can be verified in various settings. But in any case, in the literature, it's about B side. That's due to these people, and we believe that. I believe that. Maybe I shouldn't really talk about other people, but in the Calabi-Yau setting, we should have p-adic integrality. Okay. But that's for a different kind of convergence behavior, right? You mean, I mean, right. But that's about Krasner analyticity, and it's not exactly p-adic integrality, right? Okay, sure. Okay, according to Jay. So I should mention Smirnov. Okay. Andrei student, Andrei Smirnov. Andrei student, Andrei Smirnov. Okay. Cool. So now let me move to the next part. So we prove this conjecture in the setting of toric Fano varieties. So I'm going to indicate some ideas entering the proof. So let's look at toric Fano setting. So overall, the proof is based on translating that into some B-side statements. And on B-side, we're going to deal with twisted around cohomology and the corresponding connection. And there we have some ansatz following the earlier work of Dwork and other people of constructing Frobenius in a particular way. And then the goal would be first proving that it satisfies overconvergence. Secondly, also showing that Frobenius has a behavior that its initial term, after translating back to A side, is going to give you the p-adic gamma class. So that's the overall idea. So let
tell us anything about why you came up? Sounds like it logically makes sense, but you told us nothing about why.
Right. I guess okay, it's like a personal historical review. So Smirnov posted this paper on, yeah, I should really mention Smirnov. You have a good point. Smirnov posted the paper back in the summer of 2024. He studied not actually in this context of differential equation, actually difference equations. That means that, well, things come from quantum K-theory. He looked at the quantum K-theory of cotangent bundle of practice spaces. And then by writing something very similar to what I wrote here, some kind. So you look at fundamental solution, you raise the variable to its p-th power, and you look at the composition of the following form. It's going to be some kind of series. And in that setting, he proved that this series satisfies some good convergence property, and I think that's called Krasner convergence. In some sense, means that although you work with p-adics, if you do a mod p to the n reduction, this function is going to be a rational function. So that's kind of stronger. But that's his result in the setting, also using a different kind of setup involving, say, counts of quasi-maps, and it's computational in nature. So that's one motivation. And then another motivation is in this kind of Calabi-Yau setting that people formulate some integrality conjecture of this Frobenius intertwiner. And this conjecture came out from trying to understand what they really proved. And also, for example, the work of Dwork I mentioned in the case of CP1, also Sperber in CPN, in some sense, it was also featured in Smirnov's work, in the sense that he said something about you could see the work's construction from this different point of view based on his study in the quantum K-theory context. And also there are some indication in Smirnov's paper that you could see something like the p-adic gamma function looking at the initial term, which kind of similar to what Dwork wrote in his paper, but it's also clear. So, but it is the case that Dwork's work was also pointed out explicitly in Smirnov's paper, and the work's work, of course, is about overconvergence. So it's about gathering these ideas together, trying to formulate things in a precise way.
Can I ask a follow-up?
Okay.
So should I think of this as some kind of shadow of some kind of factorial formulas? Like, if you do like Feynman diagrams, you get some kind of factorial formulas. Or
okay.
Should I think of this as like some kind of shadow that we can access for?
I think I can already answer this question, but maybe someone in the audience can tell us. I don't know. Yeah.
Something a little different, but in classical mirror symmetry,
right.
One thing that the gamma function was further matching the integral structures on the
right.
side.
Mm-hmm.
There, anything? I guess we have an A in this side.
Yeah, I guess it might be something like, I don't know, integral structures in crystalline cohomology. Maybe Dan knows it's better. I don't know.
Yeah, well, maybe like an overconvergent.
Yeah.
Frobenius is sort of a p-adic analog of a
Mhm.
Hodge structure. So this is in some way specifying.
Mhm.
Could be thought of as specifying the integral lattice. Some analog.
Anyway, my point is, we try to come up with a conjecture of making things precise. So I don't want to go in a different direction, try to make things very imprecise. So anyway. All right. Any other questions about this context or whatever? Okay, I have 9 more minutes. So I'll just indicate the key points in the toric final setting. Yeah, maybe let me just write down the sketch. I just said in words. So the step 1 is about translating to a B-side statement. So roughly speaking, the mirror symmetry we're going to use is the following form. So let's say we work with the toric Fano variety. And let me call the divisors, toric divisors, di, I going from 1 to n. And the dimension, complex dimension of the manifold to be small n. And we work with the following version of Novikov ring. So lambda is equal to, say, some completion of some multivariable version of Novikov ring. So each divisor corresponds to a variable q. So there are going to be n variables. Big N is the number of divisors, infinity. And you look at the locus where the sum of these exponents is non-negative. And the mirror ansatz we're going to work with is going to be the complex torus over here. And it's equipped with the potential, which comes from counting mass of index 2 disks. So one contribution from each divisor. Where EI is the primitive integral vector corresponding to the divisor. So then the proposition we're going to use, mirror symmetry statement, is that there is an isomorphism of D modules that goes from the twisted drum cohomology twisted by this potential to the cohomology of the manifold with this coefficient. And both sides are equipped with connections. So on this side, the connection is of the form Q partial Q plus W. And here is equipped with a quantum connection. And I guess the point to highlight here is that here the exponents here are non-negative, because on the A side, to really pass to the initial term, we look at this kind of Q filtration and look at things which are defined for non-negative exponents for Q, and we want the corresponding statement on the B side. So that's why this mirror symmetry requires some sort of refinement that we should work over this ring instead. And the idea of the isomorphism follows from some early work of Iritani, and it's based on looking at shift operators. In any case, the point is that we want the statement on the A side. So quantum D module has a overconvergent Frobenius intertwiner, and the initial term is given by p-adic gamma class, some variants of that. And now we have this isomorphism, so we turn that into a problem of constructing a Frobenius intertwiner for the connection on that side on twisted ground cohomology, and we want to compute this initial term. Okay. So this is a passage to the B side. And step 2 involves constructing Frobenius on the twisted ground cohomology. And also we need to evaluate its initial term. So compute. So we want to set up so that we want to multiply things by the Dwork exponential, but we also want to set up to be in a way that it includes the Dwork exponential, but excludes the order exponential. We need that because if we're in a setting just like in the formal power series setting, that exponential functions are legitimate, then this twisting or untwisting, it doesn't really matter at all. But that's not the statement we want. So that's why for the first step here, we have to work with a slight refinement of the cohomology. So we need to work with some analytic version. So work with some cohomology theory over some Banach space, Banach algebra. And we introduce algebra, so let me repeat the point, to include the Dwork exponential, but to exclude the order exponential. And I won't get into detail of these coefficients, but let me just write down some formula which might be interesting. So roughly speaking, the Frobenius intertwiner is constructed in 2 steps. The first step is based on looking at multiplication with some variants of the Dwork exponential. So remember, our mirror ansatz have this form. So one variable for each Dwork divisor, and we look at mass of index 2 disks. And the Dwork exponential, we can apply that to each monomial of this potential and multiply them together. So the multiplication is going to be with this following function. Look at this guy. Okay. And the second step is that there are some kind of operation like applying the Cartier transform, something like that. So then there's a step of some sort of Cartier isomorphism. Anyway, the key point here is that on the B side, once you write things in this way, you can just check directly that it satisfies the Frobenius intertwining relation. And also, the Dwork exponential is crucially featured here. Okay. But this step is not refined enough to guarantee we have an overconvergent Frobenius. And the step 3 is based on refining the coefficients of cohomology coefficients, to get overconvergence. So roughly speaking, instead of working with this so-called Banach algebra that I mentioned in the previous step, we work with a smaller coefficient inside there, and we can show that the Frobenius intertwiner constructed in the previous step actually preserves a smaller coefficient we work with. And these coefficients are constructed in a way that as long as something maps that those coefficients to something similar, it has convergence property. And so that requires some computation. Right. And roughly that's the idea, but it's really hard to make things precise because the original plan was Paul was supposed to give the first talk discussing ideas. I can provide the proofs in toric setting, but anyway, this is just giving a taste of how things look like. Okay, and there's a part 4 of this, but it's just about some general speculations. Maybe I would just say that in words. So we proved things for toric varieties, and for Grassmannians, there's something called a quantum syntactic correspondence, telling you how to go from products of finite spaces to Grassmannians. So we can just go from toric statements to statements for Grassmannians. There are some other examples which may also work, like this flag varieties or co-minuscule flag varieties. Maybe that's the translation, but maybe there are some other things one can prove. In any case, I think there should be a larger class examples one could check that the conjecture hold. That's one thing. Another is that ultimately, I think this should be related to what Simon taught us about in his lecture. The geometric source of all these Frobenius structures should come from some shadow of the sectomic structure on Hamiltonian Floer theory. But making things precise and also getting concrete statements, I think that's a long way to go. So let me stop here. Thank you.